In this video, we'll talk about stress-strain diagram and how this diagram will link to constitutive equation and equilibrium equation. Alright, and therefore to start, I'll just start off with a stress-strain diagram as shown over here. Alright, this stress-strain diagram in the y-axis is strain. In the x-axis is strain. Alright, in the y-axis is stress. Alright, as shown over here. Correct? Over this region is linear. And if you know linear is equals to some stress is equals to k strain, right? And this k is some constant because it's linear. So you know 2 times this one is equals to y. So therefore it will become a linear, something like that. But anyway, linear is will have this system right here. Alright, and k is simply the scalar of how many times it is, and this scalar is in fact a constant E, or the Young modulus of the material. So a different material will have a different stress strain curve. Alright, for example, these materials, mild steel like that, iron, there is totally no linear, rubber, something like that. So different material, different stress strain curve. And this region is in fact the elastic behavior, right? Meaning it will not deform permanently. Alright, so it will never deform permanently. However, the yielding and the rest will deform permanently. Okay? And therefore they are called plastic behavior. Because if you know that plastics, if you shape it, the plastic will always be that shape already. You will not change. Elastic sounds like a rubber band. If you push it, it will actually come back to its original shape, something like that. Alright. For what is engineering stress and strain and true stress and strain? True means that it is reality, it's real. Engineering means that it was just only looking at certain graph, we predict it will fail, right? And therefore, when you do prediction in terms of engineering, which is what I have shown you in this graph right here, this is actually engineering strain and stress, alright? And therefore the true stress is often higher than the engineering stress. Alright, because we know that the true stress may be higher than the engineering stress itself. Okay, while the true strain is smaller than the engineering strain. Why does the strain smaller for the true strain? It's because this means that your elastic region will actually be decreased. Your region may actually be here only. Alright, so so the material itself may actually become more easier to be deformed permanently. Alright, so in reality the system may actually deform faster than you thought, or deform permanently faster than you thought. So the true system is somewhat very unpredictable, and is more unpredictable than, and therefore the true stress is always worse than the engineering system. That's what it is trying to say. Alright, the true, or in the reality, is always more dangerous than the engineering, meaning higher stress and more strain means that you're gonna deform faster, or you're gonna fail faster, something of that meaning. If I were to come back here, stress is equals to Young modulus times the strain. Alright, this is what we have done, and we can call this, the constitutive equation. Alright, this equation describes what constitutes the material. Alright, it describes how its stress and strain state may occur, something like that. So it describes what constitutes the material, and that's all. Okay, it's the information on the material itself. Now, when we come back here, we say that this region is elastic behavior, and then this whole chunk is plastic behavior because it will permanently deform. This one, elastic behavior, it will deform, but it will go back to its initial state. Alright, but why are they being studied? Later on you will know why, but now you will know why. It's because in our design we want to resist the permanent deformation under a certain applied stress. If you have permanent deformation, you're going to change the shape of a certain structure, and in a long time the whole structure may actually fail. So therefore we are actually looking to prevent any permanent deformation to occur if possible. Alright, and therefore we focus on the elastic properties, or the elastic region as shown over here, because this region at the highest peak itself will give us which is the level of stress before it will become permanently deformed, something like that. Alright, however, in manufacturing, this is a different case right now. In manufacturing, we have a raw material. Alright, this raw material, it comes with in a fixed shape, maybe a cube, and we need to deform it and then to reform it to a required shape. So we are trying to look at how to deform it in a way that it will not break or whatsoever. Alright, and therefore in manufacturing we are talking about plastic properties, because we want to try to see how do we do to deform it in a way that we want, something like that. Okay, this is why in the later part of our video, in the next few videos, we'll talk about elastic behavior. Right, because in our course is talking about design. Maybe later on we'll talk about this, I don't know. But now we'll focus on elastic behaviors. So elastic behaviors, the first thing, alright, is actually equilibrium equation. What is equilibrium equation? An equilibrium equation is something like that. If I were to press onto this cube that is lying on the table right here, alright, most likely the case is that there will be an opposing force acting against this force that is applied, right? So for example, if I were to apply a 5 Newton force, alright, this one will have a 1 Newton opposing force to resist the deformation, correct? And if there is a deformation, then okay, then never mind, I'll just continue first. So therefore, if there is a resistance in there, then this means that 5 minus all this resistance, if I add it up in because it's going in the opposite direction right here, so it's just simply minus 5 is equals to 0. Therefore it is equilibrium, because what is input, alright, and what is output are the same, alright. In other words, the input is equals to whatever output, and that's all. And therefore it's equilibrium. We didn't have any loss of energy or gain of energy somewhere else, so it is somewhat equilibrium. Alright, take it like a conservation of energy, or if you still remember in other stuff, summation of force is equals to mass times acceleration. Alright, so if I have to bring this one forward to the other side, we will have this form equals to 0. So the summation of force minus the moving of the acceleration of the mass will be equals to 0, because when certain mass is moving, there will be other forces acting on this mass itself, and yeah, anyway, so everything equates to 0. It's just equilibrium equation, that's all. It's the conservation of energy, something like that. Okay, and therefore in terms of context, we will still use back the constitutive equation. Alright, what constitutes the material? And this is the stress. Alright, a stress is that it is a 2 second order tensor. Alright, 3 by 3 matrix. Okay, and therefore this second order tensor, we have been talking along in the tensor videos previously. Alright, sigma, the first number is simply talking about the plane. So it should be this plane actually, perpendicular to this x1 in this one direction. Alright, so we have this plane over here, the one direction is over here. If I have the second direction x2, for example, then the plane perpendicular to x2 is this one, and therefore it's talking about here right now. Alright, and the force acting on each of on this plane, for example, if I were to have a force, or this is this is x1, alright, and we have a force that is acting just in this direction, then we can call this as sigma 11, a stress 11. If it's acting in this direction, alright, same as this axis over here, so you're actually moving this, you're actually sharing this piece of plane to this side, alright, so you actually shear it to this side, and therefore sigma 12. And if you were to pull it in this direction, which is in the x3 direction, you're gonna shear it in this direction, alright, and therefore it will become like this shape, like this, alright. And this information given is simply called the stress state, because it's telling you the state of the stress, alright. This number is telling you at this point how much stress have you been taken, at this place how much stress have you been taken, alright. So this is simply talking about the state of the stress itself, okay. And this stress state is also the stress tensor, alright. So therefore what we have been talking so far is actually talking about the stress of a certain system. This is the definition of stress, alright. This is the definition of stress, and that they are symmetry, alright. This is the same, and this is the same, and this is the same, you see. And therefore sigma 12 and sigma 21 are the same. This one is the same as this one, and I really don't know why they are the same, but just take it. And this diagonal one, alright, is the normal stress, because it's perpendicular to the plane, right? Sigma 22, sigma 11, and sigma 33, they're all perpendicular to the plane, so they call it a normal stress. And the rest of them over here, they are just called the shear stress, as we have proved just now, alright. Okay, so far we talked about all this, and we haven't talked about how to apply the equilibrium equation. What is this in the stress system, and how do we do this? In an equilibrium system, we group them by planes, meaning at this particular plane, okay, it should be equilibrium. There will be no changes, or meaning not no changes, but rather than equilibrium, meaning something apply or do here will affect these two vectors, alright, something like that. So they're all equilibrium, alright. So in other words, the stress itself doesn't, if you input more, you'll resist more, something like that. I don't know. Yeah, this is something of that meaning, okay. So therefore so we actually split them plane by plane, and each value over here, alright, this is x, this is y, this is the z axis, alright. So it's the changes in this x1, I would say. Maybe I shouldn't say x, y, z, I should say as x1, x2, and x3, okay. So this is the changes in this direction, and this is the changes in this direction, and this is the changes in this direction. So the summation of them should be equals to 0, and equals to 0, alright. So therefore it's not straight away equals to 0, but rather than their differentiation, alright, their partial differentiation across this their individual axis should be 0, alright. And therefore I have this, alright. So this now I actually partial differentiate each of these stresses based on their axis, and their stresses along this axis, how much they deform, alright, should be equal to 0. They should be equilibrium, alright. In fact I don't know the meaning, alright. In fact I don't know the meaning, the true meaning to visualize this equilibrium equation, but just to convey in the easier method is that the input force or whatever thing must be equals to the output, alright. So the output minus the input is equals to 0. So this relationship is somewhat in this form, alright, although it should be plus lah, but this plus is talking about the vectors. So these are vectors. So their vectors may initiate a certain form of position at each of this plane, I would say. So the position will change. For example, if I were to have a applied force over here, this whole thing may actually shift. Alright, or maybe they shouldn't shift like that, but rather than like that. So when you apply a force onto this plane, you're gonna compress the surface over here, and you will actually bend. And this bending is based on all these vectors. Alright, all this positioning, it will define all the position. Something like that, I don't know. It's for you to think about it. And yeah, you have to find all this. This is the thing about the summary of this video. And I'll just paste it in the description below. I'll see you there.